Hello, and welcome to part one of our webinar series, High Performance Java, Powering Your Serverless Resources. My name is Brian Beiser, and I'm a Java Solution Advisor here at Oracle. Together with my colleagues Gary Wolf and Scott Segman, we will discuss and demo serverless computing with the intention of providing a foundational understanding of the key concepts. So let's take a look at our agenda. We'll touch on the evolution of serverless and how we got here, provide an overview of the key components and workflows, provide best practice recommendations around building functions and discuss what exactly is a function, and discuss the benefits organizations are trying to achieve as well as the challenges they face. We'll introduce you to GraalVM and how in leveraging this technology, we've been able to assist many customers address just those challenges we'll be talking about. From there, I'll hand it over to Gary to provide us with a demo of the technology we're discussing today, followed up with some time for questions and answers. So please feel free to pop any questions into the chat or save them until the end, and we will make sure that they are addressed. I am going to briefly leave our safe harbor statement on the screen for your review. If any of the technology mentioned today is discussed as a roadmap item, the development effort remains at the sole discretion of Oracle. So with that out of the way, let's get started. When I first started working in technology, it was maybe 20 or so years ago. Every server required not only a dedicated piece of hardware, but there was a lengthy and specialized process, including a number of different siloed teams. It had to make its way through procurement and then be unboxed and racked. There were components to be installed, hard drives and cards and firmware updates. We had to deal with cable management and configuring the network, et cetera, all of these steps before even installing an operating system, then patching it and all of the maintenance and ongoing issues with that as well. And no matter how much baselining or planning we did, more often than not, we found resource utilization falling into one of two camps. Everything was either highly overused or highly underused. So for example, we would have a file and print server or maybe a web server, and their memory and CPU would never touch 10% utilization. But conversely, we'd have these big SQL boxes and application servers that were constantly pegging at 80, 90, 100%. And the response there was to start the process all over again, basically just throw more resources at it. So fast forward a few years and hypervisors start taking over data centers. And by abstracting away the hardware layer, we could skip that lengthy procurement, racking, et cetera process and just spin up a new server on demand, which was a great evolution at the time. The next step in this journey was highly affected by the push to the cloud. So by leveraging containerization technology, developers were able to focus on the app containers and the code itself without worrying about any of the underlying infrastructure. Now, serverless is just the next evolutionary step. So abstracting away everything else and focusing just on the code. Now, this brings us to our first benefits. By focusing solely on the code, it speeds up development times, time to market, remove the need for expensive expertise in managing the underlying systems, et cetera, et cetera. But we'll get back to benefits a little later on in the webinar. So I think a good place to start is defining the basic piece of serverless computing, and that's a function. And then within the context of a function, what does a simple workflow in serverless computing look like? So functions at their simplest definition are single-purpose pieces of business logic which make up an application. In the world of serverless computing, your team can focus solely on developing that code or building functions. And this is the first step in our serverless workflow. So you would then take that code you've developed, build it into a container, push it up to your cloud provider's registry, configure a trigger, and a trigger is just what is going to invoke your function, and that's it. From there, we get to the next benefit, which is around cost. We are just billed for our cloud consumption or cloud utilization costs. So we can see the process itself is very code-based. Your developers are focusing their time and efforts only on developing code. And at the end of the day, this will hopefully end up saving your organization money. Now, the two main components are what we just talked about, and that's functions and event triggers. So just a couple of things to keep in mind about both. Functions are by request, and when a user makes a request, the function is then started up, does its job, and then is automatically killed. So functions need to be both stateless and ephemeral. We do not want to create functions or think serverless when we're thinking long-running processes, legacy applications, things like that. So if you've done any reading or you have any hands-on practical experience with functions or serverless computing, you'll probably be familiar that most of your cloud providers have an offering within the space, as well as many third-party organizations as well. So things like AWS Lambda, Oracle Functions, Google Cloud Functions, et cetera, et cetera. The next piece that we talked about was how we invoke those functions, and those are event triggers. Now, event triggers can be kicked off in three different ways, and they can be in response to lifecycle events, external requests, or via scheduler. Now, a scheduler is just as it sounds, kick off this function at this date at this time, and it's ideal for things like report generation or reconciliation jobs. Object state changes like uploading a new file, insertion of a record in a database, or maybe a tagging event is the second way that we can trigger a function. And the last way you can invoke a function is with an HTTP request. So you can use HTTP triggers to build serverless APIs and respond to webhooks. Now, what else do I really need to think about when I'm creating my first function? First off, you want to break up your application into simple tasks. If you have multiple dependencies, it'll take longer to instantiate. So simple tasks equal a decreased execution time and overall optimized performance. Also keep in mind, there's no need to recreate the wheel. When possible, leverage services from your cloud provider or other third parties. You can greatly reduce time to market and development efforts by leveraging services for things like authentication, database management, et cetera. And also, don't forget your cloud provider handles auto scaling. So there's no need to put a ton of thought into over or under committing resources. For every new request, a new instance is spun up and then quickly killed when complete. So we don't need a ton of services consuming resources, running idle that we would be paying for. And at the same time, we need to make sure that those cold starts are reduced as much as possible so we get the best end user experience possible. We've talked about a couple of the key benefits organizations are looking for when they talk about serverless initiatives. But let's just kind of go through that list as well as start talking about some of the challenges. So the first one's going to be around reducing cost. By removing the need and expertise and cost involved in managing the infrastructure, by leveraging auto scaling and not worrying about overcommitting expensive resources. And you can really optimize your resource utilization and hopefully see a decrease in your operational costs. Reducing time to market and simplifying the deployment process is achieved by leveraging third-party services and simplifying back-end code, which allows for quick modular-based releases. What about the challenges? Why isn't every new development effort serverless? Since we help minimize expense by minimizing the resources required to run our applications, we definitely need to focus on startup times and CPU and memory utilization. To truly find the cost benefits of serverless, we need to work towards lightning fast startup times, quick shutdowns, and optimal memory utilization. Taking even a few hundred milliseconds to start up can make for a subpar end user experience, and leaving services running is just a waste of compute cycles. So how do we really find that middle ground? And I think that's where GraalVM fits in perfectly. So for those of you not familiar, GraalVM is a high-performance runtime offering development organizations a number of benefits through every step of your cloud journey. There are two optimized compilers, one JIT compiler or just-in-time, which helps customers optimize code for those ones not suited for containerization or for serverless, those long-running legacy applications. And how do we optimize the resources there so we don't go back to like when I first started working in IT, and we just kept throwing more resources at the problem. And the other one is going to really be where we focus for this conversation, and that's the ahead of time compiler. Now, this compiler converts Java bytecode into native machine code in standalone executables. These lightweight, optimized native images are not just ideal for both containerization and serverless computing because of their small footprint, but they help improve security and, most importantly to this discussion, optimize resource utilization and provide near instantaneous startup times. Now, while Gary will dive deeper into this during his demo, I wanted to share some benchmark testing that we've done around startup times and memory specifically with GraalVM. Now, the green bar represents a native image running on Hotspot, while the red represents GraalVM native image. You can see that depending on the framework that we're leveraging, we can realize startup speeds at almost 100 times faster than those compiled on Hotspot. Same thing around memory utilization. Running on Quarkus, we're able to achieve 10 times memory utilization savings. We're working on updated benchmarks around Spring and should have them shortly, but we do have integration points with whatever technologies you're using today. But I hope what you can take away from this is see that by leveraging GraalVM in your serverless, containerized, or even legacy environments, you can start to truly achieve the benefits at every step of your cloud journey. With that, I'm going to hand things over to Gary to help us visualize what we had just discussed. So please take it away, Gary.
Thanks, Brian. Today, we'll walk through a basic example of creating, building, and deploying a function. In addition, we'll benchmark performance of a jar-based function versus a native image-based function and compare the results. So let's get started. As Brian described a moment ago, there are a few basic steps for creating a function. First, we create a function template and edit the code. Then we build the function. Next, we deploy the function, and then finally we invoke the function. And this is the process we'll use today for our demonstration. In fact, for our demonstration, we'll be using technology provided by the FN project, which is an open source container native serverless platform. Let's begin by starting the FN server. By the way, you can download FN server and the client from fnproject.io. FN Start runs FN in a single server mode using an embedded database and a message queue. You can choose to start the server with a logged level of debug to display any events, warnings, or errors. Let's go ahead and start our server. To check your FN version, execute FN version. Once the server is started, we can move forward with the creation of our function. First, we'll need to create an app, which acts as a top-level collection of functions and other elements. So I'll create a directory called FN demo. I'll cd into that directory. And then we'll create our app using FN create app. And we'll call our app FN-demo. FN list will display any apps that we have created. Now that we have our top-level app created, let's add our function. We'll use the fn init command to create our function. Now, you can use virtually any language runtime, Go, Node, Python, Kotlin, .NET, but for the purposes of our demonstration today, we're going to use Java, specifically Java 17. We're also going to use a trigger. Now, triggers are pointers to functions. It's an endpoint where the function can be invoked. You can have multiple triggers pointing to the same function, but HTTP is a permitted value. Hello world will be the name of our function, as well as the directory for our function. Let's cd into that directory. And with the tree command, you can see that init has created the source for our basic function along with a POM file and a function.xml file. The function.xml file contains information such as the name of the function, the version, the runtime we're using, both build and runtime images that are used, the command for the function itself, and any triggers that we created. And for those that are curious, here's the basic hello function code created by the FN init process. Now, one more item before we build our function. Let's explore context. FN context stores configuration about your functions, the FN server, and the location of your container images. You can configure multiple contexts for your function development. In fact, I can add my registry username to the default context using the fn update context registry command. I'll go ahead and add my username, and we'll list the context again. As you can see, my username has been added to the default registry. The next step is to build and package our function. And we'll accomplish that using the fn build command. I'm going to use the -v flag option just to display some additional information during the build process. The end result is the function is built and a new container image is created. In this container image, the application jar file is packaged as a layer of an image containing that Java runtime environment. Okay, with our function created, the next step is to deploy our application. Within the function folder, execute fn deploy. We'll pass the application name, and we'll use the -- local flag. The -- local flag will skip the push to a remote container registry, making local development much more efficient. This command deploys the app to the local FN server and links a trigger called Hello World to that function. We can also display a list of our functions using FN list. And we can inspect details of our function too. The inspect command allows us to display properties of our function. And finally, we can invoke our function. We'll use the fn invoke command by passing the application name along with the function name. As you see, we returned hello world. Now, with this function, we can also pass a string, and it will substitute that string in our output. So we'll go ahead and pass functions to our hello world function. And you can see world was replaced with functions. Now that our function has been created, let's run a benchmark to determine how our function is performing. We're going to use Hey to generate load for our function. For this example, we'll generate a load simulating 1,000 requests and 100 concurrent workers. And we'll pass the function string to the endpoint, like we did in the previous example. So there's the 1,000 requests, 100 concurrent workers. We're passing functions. And then here's our endpoint. Now, it's going to take a few minutes for this benchmark to run. Within the results of this benchmark using our jar-based function, I'd like to draw your attention to the number of requests per second, which in this case is approximately 54. In addition, I'd like to highlight the latency distribution, specifically the 99th percentile, where 99% of those responses occurred within approximately 12.7 seconds. We'll come back to these numbers later. Now, as a comparison, we'll create another function, but this time, instead of a traditional jar application, we'll utilize the ahead of time or AOT compiler feature of GraalVM to create a native image executable of our Hello World function. As Brian described earlier, the GraalVM AOT offers exceptional performance and startup times, and these characteristics can be realized with functions too. We'll follow the same process to create the native image-based function, although our init command will be slightly different. We're going to pass a --init--image command line option to specify which container image will create our function template. And in the following example, we're using the GraalVM Enterprise Edition image based on JDK 17. So we'll cd up a directory, and then we'll go ahead and run our init command, passing the --init image, and then identifying the GraalVM init image based on JDK 17. We'll use the same trigger. This time we'll call our function Hello World Native, and we'll also call the directory Hello World Native. Now that our template is built, once again we can build our function using fn build. Next, we'll deploy the function using fn deploy. And finally, we'll invoke our function using fn invoke. And we get the same output as expected. Now let's run the Hey benchmark once again using the newly created native image version of our function. we'll use the same parameters as we did in the previous example. 1,000 requests, 100 concurrent workers. This time we'll pass native as a string to our native image function. You'll notice how quickly the benchmark ran. And once again, focusing on requests per second, you'll notice the requests jumped dramatically, up to over 6,700. In addition, we see the same impressive result with our latency distribution at 46 milliseconds. Also notice the size of our containers. The native image version is approximately 1/3 the size of the jar image, 149 meg versus 488 meg. And I realize sometimes it's difficult to see the output of the benchmarks in a terminal screen, so I've created a chart describing the requests per second, or comparing the requests per second for both the jar version of the function and the GraalVM AOT version of the function. And as you can see, we went from about 28 requests per second to over 4,100 requests per second. Likewise, the latency in the 99th percentile went from 18.38 seconds to 45 milliseconds. And of course, once again, just to review the image size, the jar version of the function was 488 meg, while the GraalVM AOT version is 149 meg. So we're seeing pretty impressive results on all fronts. Well, that concludes the introductory demonstration of functions. With this simple example, you can see how easy it is to build, deploy, and test, even benchmark functions written in Java. And with GraalVM AOT compilation, or native image, you can achieve even better performance while reducing resource utilization. So now's the time for you to begin exploring and evaluating Java and GraalVM for your serverless use cases.